right, here, let's get our bearings. We were in lecture 8.4 on slide 33 out of 121. Of course, you won't have 121 slides in your thing because these, go step by step. But there's still lots of stuff to talk about with when you have this weak acid, strong base, and then we're going to get into what happens when you have a strong acid and a weak base, and then a little bit about weak. So let's figure out what's going on with this stuff. We left off at this problem. There's several steps problem. Hopefully you guys are getting really good at writing these reactions and the net ionic equation for these things. And we're going to throw a little curveball in the situation this year, or in this next lecture here, which is the third of I don't know how many lectures for 8.4, but it's called the Henderson-Hasselbalch equation. And this is in your purple sheet, pH equals pKa plus the log of the quantity A minus over A. And you remember, HA is representative of an acid, and it's very important that you know that this is going to be the concentration of the conjugate base of that acid. That's why they use those terms. So saying base over acid falls a little bit short of what it's really getting into. What you want to have is this weak acid with its conjugate base, and we're going to find out that is something called a buffer. And just real simply, a buffer is something that doesn't change pH when you add hydrogens or when you add hydroxide ions. So interesting thing to keep in mind. All right, so just remember that weak acid and its conjugate base. All right, so these equations, again, are things that we talked about briefly. So negative log is what the P stands for. And then if you have the Ka, if you have the pKa and you want the Ka, then you're going to raise 10 to that power, the negative power of that. So we will see things like that. So here we go again. This is example number 5, weak acid and strong base. So volume, concentration, different volume, different concentration. Here's your weak acid, and we know that you have a pKa value of 4.8. And then it says, given this information, what is the pH of the final solution? So, if you remember, and you might want to just try this to see if this comes back to you, how to write the equation for this, the net ionic equation. So remember the OH, you're really not concerned about the K because that's a spectator ion, so you just write OH, and then you write the acid with the hydrogen intact. I told you, those of you that I had in class, I used a salt shaker instead of a shirt. So this acid wants to keep that hydrogen, but along comes the bully OH and says, give me that salt. And so this poor acid doesn't have his little salt shaker anymore. Works better with a shirt and a very cooperative volunteer to fight for the shirt. So thank you for doing that. Anyway, you end up with right here, this is the conjugate base of that acid, and then water molecule. All right, so we're going to find the limiting reactant. Your gut is going to take you home again on this because you're like, they're all over the place. How am I supposed to know how much of what is going on? Well, you convert it into moles, and you take that volume, use the molarity as a conversion unit, and then the ratios within the balanced chemical equation. So that's a stoichiometry problem. You can stop at moles because that's the goal in this case. And then, so here you have your 500 milliliters and a little stronger concentration of that. So you end up having quite a bit more of the conjugate base in this case. So then our limiting reactant is the KOH. So the bullies are the ones that are limited. All right? So now when the weak acid is the one that there's excess of. Okay? So now you got a bunch of these acids going, I still got my salt shaker. There's no more bullies to rip it away from me because they're gone. Well, the thing is, you don't necessarily, it's a weak acid, right? So sometimes this guy says, yeah, go ahead, take that salt shaker. It's not maybe, and that's a whole spectrum of things, right? As to how willing they are to give that salt or shirt away. So some of them, some particular acids will be very, very weak and almost impossible to get rid of that. And some of them will be like, yeah, you know what, take it. Yeah, I'll take it. And, you know, so that's where we have to be able to quantify this, and that's where the Henderson-Hasselbalch equation comes into play. So what you need to do is figure out the acid conjugate base ratio that we're going to be talking about for this particular solution. So we know what our value was for the moles of OH, and this is just, again, since it was a 1-to-1 ratio, that was our limiting reactant problem. It ends up being the same numbers because the 1-to-1 ratio, that was that extra step, didn't change anything. But you really are, you know, you're doing a different thing here. You're just saying 2 liters and you're converting that into moles, 5 liters and you're converting that. So that gives us our values that we need for doing the calculations that are coming up here. So if you want to figure out what the concentration of the conjugate base is here, then you have to say, well, I got to take the moles over the total liter. Okay? So the moles over the total liters is that many moles, and you divide those out and you get 0.43 molar is the acetate, which is the negative ion here. And if you want to figure out what the acid was, you have to take that original concentration minus the 0.03. So you see the difference there. This one was the limiting reactant, so that was predictable. But this one, of all of this stuff, you know, like we said, how many of these guys are walking around holding salt shakers? Well, 0.5 minus that, and then you figure out the concentration that way. So really, you got to put some thought into what was going on in doing this. Okay, so this one is predictable because this is the one where it was, you know, ripped off by those OHs, which are all gone now. All the bullies are gone. So find the pH of the final solution. Well, you got to use the Henderson-Hasselbalch equation. pH equals pKa plus the log of the acetate over the acetic acid. So those values we just gave you, the pKa was given to us as well. So this will involve probably a parenthesis key on your calculator, but make sure that you crunch those numbers and that you can get this negative 0.60, which of course is going to bring that down to 4.2. So not unusual for that pH to be very close to the pKa values in these types of problems. Okay, so because this change factor is usually relatively small. All right, so hopefully you got that. Get some good notes about that. Here is yet another example, and the thing that you will notice about this example, and this really changes the game, is that you have 300 milliliters of a 0.5 molar and 300 milliliters of a 0.5 molar. So now everything's even. There's going to be no excess bullies. There's going to be no excess weak acids. Okay, so it becomes more straightforward. But of course, you can write the net ionic equation. Nothing's going to change for that. The same general type of rules are used there. There's your base, there's your weak acid. So that part is the same. So now it says, find the concentration of that acetate. Well, since these are equal, you can start off with this concentration of the acid, which there was 0.5 moles of it. And this is in a 1-to-1 molar ratio, so there's this many moles of the acetate. And that's produced because all the COOH reacted, and it did that because there was exactly enough bullies to do that. So you can predict that the amounts will be the same. So it actually makes the problem easier, but you got to check it too. So your total volume is the a 30 milliliter. I think I might have said 300 milliliters before, but it's 30 milliliters. You add those up and you get 60 milliliters. And since the volumes and concentrations were the same, and then this was the moles that you just figured out there. So now you have your concentration of your acetate. Okay, so equal moles of the strong base and the weak acid have reacted, and all of the OH has ripped off those hydrogen ions, and they each have a salt shaker. All right, and only the Na plus, and remember that big discussion we had, and the COO minus. So you've got these two ions remaining in solution. All right, so those are the only things that are left. All right, so what happens is the final solution is slightly basic as the OH increases. The pH is found by using the above equation right here, knowing that you only have these guys left in the solution, and then you can calculate a Kb for that. Okay, so of those acetate ions that were left, all caused by the mean old OHs ripping off the hydrogens, we can then go to finding Kb. All right, and just out of to be safe here, I'm going to stop, because if I go 2 seconds over, I have to redo the whole video. So we'll stop right here, knowing that we need to find Kb of this reaction. So we'll be right back on video number 4.